Scikit-Learn is one of the very popular machine learning toolbox or tool developed in Python. Right? It provides us a range of supervised, unsupervised learning algorithms for classification, regression, or clustering with a very consistent interface in Python. Okay? The library is built upon on the SciPy and NumPy library, okay, which must be installed before you can use scikit-learn. So we said NumPy provides tools for working with n-dimensional arrays, while SciPy provides us the fundamental library for scientific computing. It also uses matplotlib. So what are the features of scikit-learn? Here, also the interface to scikit-learn is in Python, but low-level implementation of many algorithms uses C libraries, which means it's quite fast. Okay, and also uses NumPy for array and matrix operations. Again, written in C. You can go to the following website to learn more about this library. Okay, scikit-learn. Now let's talk about how we can represent data in scikit-learn. Okay, data in scikit-learn, with a very few exceptions, is assumed to be stored as a two-dimensional array with the following shape of number of samples versus number of features. The columns represent number of features, and then rows represent number of samples. Also, many algorithms in scikit-learn can use sparse matrix of the same shape, two-dimensional. So number of samples represents the sample, which is an item that needs to be processed. Okay, the sample can be a document, a picture, a sound, a video, or some other object or observation, which is stored in a row of a, for example, CSV file, or whatever you can describe with a fixed set of quantitative traits. The number of features that can be used to describe each item in a quantitative manner. As we know, features are generally real valued, but can also be Boolean or discrete valued in some cases. Okay, so number of samples and number of features. The number of features must be fixed in advance. However, it can be very high dimensional, containing millions of features, with most of them being zeros for a given example. This is the situation where you can use SciPy's sparse matrices for making it more memory efficient than NumPy arrays. Okay, so as we recall from the previous section, we represent samples, data points, or instances as a row in the data array, and we store the corresponding feature, the dimensions, as columns. Let's take a look at this simple example, the iris dataset. We have talked about it already. Okay. This iris dataset is stored in scikit-learn. It is available. And if you remember, we have here data that with the 4 measurements corresponding to 3 different iris flower species. Okay, for example, Iris setosa is the type of the flower which looks like this. Okay, and Iris versicolor, Iris virginica. Right, so 3 different classes, and each of these flower has some attributes, some features that we put into data or matrix array. Now let's take a look at this quick question. Let's assume that we are interested in categorizing new observations. We want to predict whether unknown flowers are Iris setosa, Iris versicolor, or virginica, iris flowers, respectively. So based on what we have discussed in the previous sections, how would we construct such a data set? Just based on these, right? So, and again, scikit-learn accepts the following two-dimensional array, where row corresponds to samples, column corresponds to features. Right? So in this case, what would be the sample? What about the features? All right. So now let's take a look how we can load this iris dataset in scikit-learn. So there is a very good repository, which is called UCI, Machine Learning Repository, which hosts many of the commonly used datasets that are useful for benchmarking machine learning algorithms. So it's a very popular resource for machine learning practitioners. So just if you go here, you'll find a lot of datasets ranging from simple to more sophisticated. So iris flower is here. Okay. So they say attributes, number of features. Number of instance means number of examples, number of samples, right? And let's see, wow, the date donated, okay, ranged back to 1988. So it was uploaded at that time. You can find some of the studies that use iris dataset. Well, it's very simple dataset. Okay, but again, take a look at this website. You can find some useful datasets. Okay, car evaluation. What is this? So car evaluation data was derived from simple hierarchical. Okay, from this study. Yeah. So just take your time and review all this. Okay. So let me go back. So for convenience, Scikit-Learn developers added most of those datasets available on UCI repository. Okay, so they come with Scikit-Learn Bundle, which allows you to skip the most time-consuming part of downloading, reading, parsing, cleaning, and putting those datasets in the form of samples versus features. Okay, in this form. Instead, you can just go and explore these module of the Scikit-Learn where they describe what data sets they provide, Boston, Iris, and some others. For example, Scikit-Learn has a very straightforward set of data on this Iris species. And data has the following information. So features in Iris dataset correspond to sepal length, sepal width, petal length, petal width. And target, since there are three classes, Iris setosa, Iris versicolor, and Iris virginica. So if you wonder what is petal and sepal, okay, petal is this part of the flower. These, I don't know if you can call it as a leaf, and this one, okay, so smaller leaves of sepal, and this is petal. So we measure the length in centimeters, okay, length, and then width in centimeters, and then length of sepal, and then width. So it has been manually measured by someone. We're not working with the image data. We're just working with the measurement of this length and width of this. In this example, okay. So how can we load Iris? Okay, for that you ask from Scikit-Learn dataset import load Iris. This is a function that allows us to load the Iris dataset. So if you run this, all right, we okay, we import load iris module and instantiate, and here we have the iris, and it looks like a dictionary data iris with the keys, but it's called as a bunch object. Okay, but similar to a dictionary, you can see what it contains. So iris contains a data field, target, maybe this is the data or two-dimensional array, target is a label or labels. Some other additional examples, okay, target names, feature names, description, and file name. So if you want to extract the shape of the data, we can say iris data shape. Number of samples, number of features. So number of samples is equal to 150. In other words, the data has been collected from 150 different flowers. And each flower has 4 measurements, 4 features, which is sepal length, sepal width, petal length, petal width in centimeters. Okay. Now let's take a look at this. The shape of the data, 150 times 4, and then we have target, 150 target. These are basically labels. This is our X, data is our X, target is our Y, right? We're dealing with a supervised learning task in this case. We can take a look at how the data looks like. For that, let me just do this. Iris data. Just if we open this up, it's a two-dimensional NumPy array with, again, the following dimensionality. We have 4 features as column, right? The features of the first flower, features of the second flower, up to 150, right? And then we can print the Y labels or target labels. three classes. So first class is labeled as 0, y, and second class is ones, okay? And then third class is labeled as 2. So we're dealing with three class classification task. So three class, that corresponds to the following flowers: Iris, Setosa, versicolor, virginica. All right. Now, if you wonder how many samples in each class are there, we can use NumPy's bin count function to count the number of classes or number of observations in each class. So 50, 50, 50. So all of them are have 50 examples, right? 50 samples. So it's not unbalanced. It's very balanced dataset. Again, class 0 represents Iris setosa, class 1 represents Iris versicolor, class 2 Iris virginica. So this will be your Y labels, X and then Y, right? Yeah, and then we can find this information in Iris target names. Yeah, since the data is four-dimensional, we cannot visualize four-dimensional easily. But we can visualize one or two dimensions at a time using, for example, a histogram or scatter plot. And we do that using a matplotlib. So don't forget to enable or just call this magic function, magic comment called matplotlib inline, and we can visualize some of the selected flowers. Okay, so what we have here is three classes: Setosa, Virginica, or versicolor color flowers with one feature. Okay, so we are just comparing the petal width, one-dimensional feature. What about this one? So we can try to visualize two-dimensional feature as a scatter plot. So sepal width, petal width. All this blue corresponds to Setosa. Okay, example. So we're just taking two features out of four. And also here we have Virginica and then versicolor with a little bit of overlap. All right. As an exercise for you, I will leave these. Okay. Change X index and then Y index. Try different X index and Y index in the above script here, and find a combination of two parameters of features which maximally separate three classes. Right. Well, we can further use different visualization techniques, such as the matrix of scatter plots. Okay, so this kind of visualization shows all the features in the dataset, as well as the histograms. For example, if I do this, what we have? Petal width, sepal length, petal, sepal length. So for example, sepal length, sepal width, all possible combinations of four different features. And also we have the histogram, the distribution of sepal length, distribution of sepal width, distribution of petal length, distribution of petal width. Well, this kind of matrix of scatter plot or scatter plot matrix is useful in data analysis generally. So we can see, okay, which features are more separable, for example, visually, right? And decide to use those after analyzing or visualizing. Other datasets. So Scikit-Learn makes available a host of datasets for testing machine learning algorithms. They come in three flavors. First is packed data. These small datasets are packed with scikit-learn installation and can be downloaded using the sklearn.datasets.load underscore. We also have usually packed datasets are very small datasets in size, such as the flower dataset, iris flower dataset. If the dataset is huge, then Scikit-Learn provides us a link to download it. Okay, these are larger datasets, but they include tools which streamline this process. These tools can be found in Scikit-Learn dataset fetch. Okay, if you call this, then Scikit-Learn dataset module will download to local directory. Right? The size of Scikit-Learn is not too big itself when you install, okay, even with these pack data. But some of the dataset, downloadable datasets, may have 1 GB of size, so it is reasonable to download them or make them available for downloading only. And third one is generated data, right? There are several datasets which can be generated from models based on random seed. And those are available in this module. So sklearn dataset.make underscore star. All of these you can explore, okay, and analyze the documents by just typing dataset, sklearn datasets dot load underscore, and then tab will give out all the dataset possible. So we can try datasets load. And then if you do this, we see a bunch of datasets that can be loaded directly. Okay, these are bundled. They are available. Breast cancer, diabetes, digits, files, iris, blood Boston, sample image, etc. But they are available. Fetch. These are the dataset that can be downloaded. Usually the size is bigger. Newsgroup, KDD COP, housing, Olivetti, these are image data, etc. What about the make? So make allows you to generate circles, moons, make regression data set, etc. All right, for working with your machine learning. And many of these data sets are quite large, usually in fetch, and can take a long time to download. Can be in the order of gigabytes. Let me show you one example of how we can load the data. So from sklearn dataset, load import dataset, and then this is handwritten digits, right? So load digits, instantiate the objects, and then key. As you can see, it's very similar to the iris dataset in terms of structure. We have data, target, some other input features. And if you wonder what this dataset is, okay, digits. If you want more details about this dataset, you just go to description, or it's better probably to print. Okay, if you look at this field, you find more details. So optical recognition of handwritten digits. You have seen this in one of our classes. There are 64 features in each example. The number of observation, number of samples is 5,620 images we have, handwritten digit. And then the number of dimensionality actually is 8 by 8. So we have 8 pixels in row and 8 in column direction, right? So range between each pixel range between 0 to 16. So again, this is the data that comes from UCI database, okay? Right. So now what can we see? So again, we can find this information. Data shape. Okay, this is the number of samples, number of features. Here we are selecting the subset of all dataset. But in documentation, entire dataset is 3 times the one shown here almost. We can take a look at the example of the one of the digits and target values. Let's see. Let me separate this. Right? So digits, data, 0. 64, right? 8 by 8 image pixel, and then the target for that would be 0. So this first sample in our data corresponds to 0. Okay, handwritten 0 digit. What about this? 1. Okay. 8. So as we can see here, let me print this out. From 0 to 1 up to 8, 9, 8. Well, it depends. Here, data shape, image shape is 8 by 8, 64 in total, each feature. Why is this like this? Because as we said, Scikit-Learn wants us to provide two-dimensional input. First entry, the rows, correspond to total number of samples. Second one is features, right? So Scikit-Learn cannot accept 70, 90, and then this three-dimensional. It accepts only two. So we need to flatten this or construct the one-dimensional feature or vector from 2D array. Okay, so if we do the rearrangement, then we can visualize. So these are the examples of the handwritten digits. They have been quite downsampled, so we cannot clearly see. So this is 2, 3, 4, 0, and etc. All right, so another example is Olivetti faces. So here we need to download the data, okay, and then visualize. So if you visualize, the Olivetti data corresponds to the image of the faces as shown here, right? It has the same information. This is the face data. Just try to download and see, explore yourself. Given the dataset represented in two-dimensional array, whether it is an iris dataset or image dataset, the next step in machine learning is performing model selection, right? Selecting the model and assessing its generalization performance. One of the first steps, as we discussed in the validation lecture, is performing cross-validation. Right now, let's just focus on training and tests. Assume this is your X. We will train your model on training set, okay, with the given labels, using the labels, and evaluate on test set. So first, let's just load the iris data set, and Scikit-Learn linear model module contains a lot of machine learning methods, algorithms, for example, logistic regression, okay, that we can use, linear regression, logistic regression, and many others. Just quick look at module, we can see, okay, we have Bayesian, Reach, Elastic Net. There are many algorithms, right? Linear regression, logistic regression, lasso. This is another form of logistic regression with different regularization, and some other classifiers. All of them, even the perceptron, all of them belong to a linear, let's say, class of machine learning algorithms. So we can use. So now just let's import logistic regression that we are familiar with as a classifier and extract our X and then Y from iris data and then target. Our X and Y looks as follows: 150 examples and 4 features. The next step would be to perform model selection. One of the first steps in model selection involves splitting your entire data into train and test, right? And we select a model based on training dataset and evaluate on test dataset. Okay, and here the test dataset acts as the simulated, unseen, or new dataset that our classifier or model would generalize. In the case of iris dataset, we have 150 examples from 3 classes. And if we split the data using a proportional split, this is going to result in altered class distribution. For example, if we perform a common 2/3 for training and 1/3 for test data split, our training data will consist of only 2 classes of flowers, Setosa and Versicolor, right? And then the test will consist of the Virginica. Well, this is not correct way of splitting the data. Because our training dataset should represent all the examples from all 3 classes. Under the assumption that all samples are independent from each other, we can shuffle randomly before splitting the dataset. Let's take a look how we can split the dataset. And the ratio of the train and test is another question. One can simply use 50% for training, 50 for test, or 80% for training, 20 for test. If you use 50-50, the amount for training dataset will be less, or the number of training examples will be less for our model to learn better from the data. Therefore, most common approach would be 80 for training, 20 for test. So we also have validation set, which I will explain later. So now let's take a look at this function called train test split. Basically, splitting the entire data and train and test is very common, and Scikit-Learn provides us this handy function. You can also define your own function, which will divide or split your trained data set into different sets. But for convenience, we can use the following. What does it do? It accepts our x and y with the following parameters. So we need to define which 50% for training, 50% for test. So these are the size of the train and test data set. If you want 80 to 20, you can change it as follows. Okay, and this is the random number generator state. And if you do that, the output will be train x, test x, train y, and test y. We have two separate examples now, train and then test. And if you look at these labels, okay, train consists of 0, 1, and 2, right? That means all of the samples of flowers have been selected as a part of train dataset. Well, another better way of splitting the data is called stratified split. Well, this is handy when you have small data set. Stratification means that we maintain the original class proportion of the data set in the test and train set. For example, after we randomly split the data set as shown in the previous code, we have the following class proportion in percent. So all 33, 33, 33 class proportion. So again, 50 example, 50 example, 50 examples of 3 different class of flowers. Training set has 30% for Iris virginica, Iris setosa, and Iris versicolor. 30%, 40, 29. Test 36, 26, 37. So the class proportions are not equal. So stratification, what does it do is to split the training and test equally with each class proportion. So if we do this again, we pass just stratify y argument to our train and test split, and at the result we'll have the following distribution of the ratio: 33, 33, 33 for all 3 different classes. Okay, test as well. Right, now we can simply call the classifier that fit function on our train data set, okay, and then train y. Well, what does it do is it performs the training of the classifier or logistic regression on our training set. Once after this step, the weights have been already updated inside this object, classifier object, which corresponds to weights of the logistic regression. We can use classifier predict on test dataset that we have allocated separately. Okay, and then evaluate the accuracy. You see, predict, we're not passing y test. Predict y consists of the predicted y, pred, okay, pred y. For each example shown here. So 1, 2, all the labels. So test and then pred. We can calculate the accuracy using the following formula. We sum, okay, pred and then test y, and then divide by total length average, which gives us 94% accuracy, which is pretty high. So we can also visualize samples that have been classified correctly, almost all of them. Again, remember, and these samples are classified incorrect. Only 4 out of 75 flowers has been misclassified, which is, okay, not that bad. We can also visualize those flowers, okay? I mean, in Calico, number of correct and incorrect classification as a part of scatter plot. So error occurs in the area where green class 1 and class 2 overlap. These 2 overlaps. This is again a very quick example of how you can perform a train and test split, but we didn't use here the validation set, which we're going to be using later. This was just for demonstration purpose as an example of a simple model selection.